If you're interested in building anything with AI agents, you definitely want to stick around and watch this video. Today, I'm going to be pushing AI agents to their absolute limit through a game of chess. I'll be using the most powerful models available to us to play a game of chess against the Stockfish chess engine. I'll be showcasing Claude Sonnet 3.5, GPT-4 Omni, and I'll also be using agent frameworks like Mixture of Agents and a custom multi-agent framework that I've come up with. If you stick around to the end, I'll be sharing my opinion on what the game of chess teaches us about using AI agents in practice. The GitHub repository containing the code for this project is open and available to you via the description to this video. So feel free to check that out if you want to use your own large language model agents to play chess. If you like this content, give us a thumbs up. Don't forget to subscribe to the channel for more large language model and artificial intelligence engineering content. All right, let's get into the details. Before I dive into showing you some examples of how these agents can play chess, I'd like to show you how to get set up yourself with this script because it can be a little complex. Now, I do have some more detailed instructions in the GitHub repo, so you should check out the README for those, but this should really be a complement to those README instructions. Feel free to skip this part of the video if you don't want to know how to get set up with your own chess engine. To give you an overview of what's going on here, most of these scripts you see on the left-hand side have been cloned from the Lichess Bot open source project. I have made a few adjustments to enable this to work with large language model powered agents, and that's what I'm going to talk through today. Everything you see is centered around just a few scripts. So the first one is the homemade.py script. Now, this is something that comes with the Lichess Bot project, and this is where you can set up your custom chess engine. So in this case, I'm using large language models. If you want to set up your own custom engine, the only requirements are that you set it as a class. It must inherit from the minimal engine, and that's something that's defined by the Lichess Bot project. And the other thing to be aware of is it must have this search method. So every engine that you set for yourself has to have this search method. So you can essentially just copy any of the engines I've created and create your own template off the back of that. As long as it has this search method, you are good to go. And then you want to obviously return the play results. This is you posting the move to the Lichess API. I have a few engines that I've created here. I have an engine that I've created just to run a single agent. I have an engine that I've created to run a multi-agent workflow that I've come up with. And lastly, I have an engine that I've created to run Mixture of Agents. Now, something else to notice with these engines is that I have several models that this is compatible with. So it's compatible with Claude, it's compatible with OpenAI, and it is somewhat compatible with Grok as well. The limit here is that Grok actually requires you to be within their API rate limit. And what happens is when you use this as a chess engine, it hits that rate limit quite hard. So I've tried to incorporate a sleep function with Grok to make sure that it doesn't hit that rate limit. What you should be aware of here is by the time I post this to GitHub, I will have this using Claude as the default. And the reason I use Claude as the default is I found that it is the chess engine that delivers the best, well, not the best, but the most consistent performance. What I found with the OpenAI engine is that sometimes it actually writes moves to the chessboard that don't exist or are not playable. And I found that this happens less with Claude. So Claude is the default model. So you'll need a Claude API key. And that's if you're using the multi-agent one. And if you're using the single agent one. If you're using Mixture of Agents, you're going to need both Claude and OpenAI API keys. What you can do is you can step into this homemade.py script, and where it's referenced get LLM response, you can change this to get LLM response OpenAI or get LLM response Grok, and change your model to a Grok model or to an OpenAI model, whichever tickles your fancy. Look, I have not made this, I haven't put a UI on top of this. It's very much going to be coding work if you want to customize this for yourself. But if you have both an Claude API key and an OpenAI API key, this thing will work as is. Once you have your engine set up, what you want to do is you can choose a particular engine that you want to run by heading into the config.yaml file. Here you will, if you follow the GitHub instructions in the README, you already have a token set up. But what you should be aware of here is under the engine argument, what you want to do is you want to set the engine that you would like to run. So this is just the name of the class that you set in the homemade.py. This isn't how I've set it up. This is actually just how the Lichess bot project works. So you can set your engine here. So right now it's set to large language model multi-agent, LLM multi-agent. And you can see in the homemade class, I have the LLM multi-agent set here. If I wanted to set it to use a single agent, all I would have to do is copy this, the name of this class, and paste it here under the engine with the name argument there. Right, so that's how you select a different engine. I have this LLMs.py script, and this is where I've defined all of the large language models that I'm going to use. So you can see the OpenAI one, and by default, that uses GPT-4o. There is one here for Grok, and there is also one here for Claude. So those are the three options that come out of the box when you use this project. If you want to add your own large language model service provider, you can add it in this LLMs.py script. Just make sure that you import it into the homemade.py script when you're creating your custom engine. The other thing I have here is the prompts.py. And this is where I'm actually feeding all of those prompts.py. This is where I'm actually feeding all of those prompts to the agents to get them to work as chess engines. And you'll see here as a standard, what I've got is I give a given chess engine an understanding of who they're playing as, so whether they're playing as black or white. I also give them an understanding of the state of the board. So actually, this shouldn't be FEN. This should be the state of the board just as is. I give them an understanding of all of the moves they've played so far. So all the moves that white has played so far and all the moves that black has played so far. And I give them an understanding of the possible moves. So every agent has those things understood. Just to give you a better insight into what this is, the state of the board is the sequence of moves that have taken place since the beginning of the game. And this is updated every single turn. There are a lot of functions within this project that help you do this. But ultimately, what I've done is I write the board state to this game_state JSON. I'll show you what that looks like. So you can see for the last game I played here, the sequence of moves that were taken. So the agent has an awareness of the sequence of moves that were taken since it started the game. If you wish, in your own time, you can go through all of the prompts in detail and see how they work with the different agent setups that I have. The last thing for you to be aware of is that you will need to set your API keys. If you navigate to the LLM_agents folder, this is where I keep the prompts.py script. This is where I keep the LLMs and also the API keys. So if you open this, you will see the API keys for Grok, for Claude, and also for OpenAI. So if you want to use any of those models within this project, make sure those API keys are updated in the API_keys YAML. I've given a description of that within the README. I'm going to run my first chess agent experiment using the Claude model. So this is the latest model that came from Anthropic, which is Claude Sonnet 3.5. Now, the way you do this, if you're doing this for yourself, is navigate to the homemade.py script. And depending on what agent you're running, so for this first experiment, I'm running just the single agent. So I'll navigate to the class that is single agent LLM. And the first thing you want to do is look for where it says model. And you change that to the Claude model. And then you want to look for where you're generating responses. So it will usually be the function get LLM response. And instead of using OpenAI, you will change that to Claude. Now, if you are unsure about the names of these functions that you should be changing, if you scroll to the top of the script, you'll see where I've imported all of the available functions as they are. So you can either use Grok, OpenAI, or Claude. In this case, we are using Claude. because we're going to be testing the Claude 3.5 Sonnet model that has just come out. Now, starting off with this model, because supposedly it's one of the most powerful models that has been released, one of the most powerful proprietary models. And Claude or Anthropic themselves state that it is their most intelligent model. So it'll be a good model to start off testing this chess engine with. So hit save. In the config.yaml, you'll want to make sure that you're referencing this single agent LLM if that's the one you're running. So just to show you that I am referencing that. And once that is all saved, you can then open up your PowerShell. So I have my PowerShell open here. And to get your chess server running, you run Python lichess bot.py. You have the option to include a V argument, a verbose argument, which will deliver all of the debugging statements. I'm not going to do that for clarity of output because I want to show you how the bot is reasoning alongside playing the game, and it would just be clearer to not have all of those outputs. So I'm not going to include that, but when you're running this for yourself, you do have that option. Then once you're ready, you've hit Python lichess-bot.py, simply hit enter. And if you're successful, you'll see a message coming up saying the bot server has actually started. There you go. So we're up and running and we are waiting for challenges. So the next step, I'm going to actually challenge a computer model. So it'll be the Stockfish 5 model that is available to you on Lichess. I'll challenge that computer model and see how well this single large language model agent can do against the computer. All right, let's play our first game with the Claude 3.5 Sonnet model. So I'm going to hit play with computer and notice our server is set up. I did run one earlier before, but something went wrong with the server, so I'm starting it again. Let's hit play with computer. So we're going to play as white, and we're playing on strength 5 for the Stockfish engine. So we're going to make the first move, and I will talk through as I see. So the King's Gambit, solid opening. And right, so we are covering the middle. Not bad so far. Let's see if we get some aggression going, maybe develop some of the bishops. Okay, so the sensible thing here would be, well, there could be a trade-off there. We are covered by the queen, so that's okay. Let's see if we can get this to safety. Doesn't make sense to sacrifice the knight this early. That's good. So we can't get rid of that knight because we'll be leaving ourselves in check. Let's see, we cover. Okay, so I think that's potentially a mistake, but it's not bad. Okay, so we've capitalized on black's mistake there. Okay, castling, not a bad move. It looks okay so far, but the game is starting to get a little bit more tricky. I feel like that was a needless sacrifice of a knight. We've lost material there for no reason. And that's a needless sacrifice of a bishop too. So here's where we're losing the game now. And it'll be interesting to see the analytics because you should see the momentum kind of shift from what was about even to now shifting towards black. We made two needless sacrifices there. Let's see if we'll move our rook to safety because it's currently under threat from this bishop. We haven't. And we've actually sacrificed the queen as well. So you can see the model is really starting to break down now. The agent is really starting to break down. And I think at this point, we are pretty close to losing. We've lost most of our major pieces. We just have two rooks left. I think from here, it shouldn't be too hard for black to get the checkmate. He's setting it up here. Okay. So we're vulnerable here. And I think it's looking probably like a checkmate too. It's most probably we're going to move here, and then that's all right. So that started off quite well. I thought, anyway, I thought I started off quite well, and it looked like it was going to be a tight game. And then the game did reach a point where the agent just seemed to break down completely. It just seemed to not know at all what it was supposed to be doing, which to me is really interesting. What I like about light chess is you can actually get the computer to give you an analysis of the game. So let's see if we can get in and get the computer to give us an analysis of the game. So let's just have a look. Here we go. So we can request a computer analysis. And what's interesting about the computer analysis is it will tell you where the momentum of this game changed. And it's at that point I want to examine some of the reasoning traces from the large language model to see exactly what it was thinking. So you can see there was a massive shift in momentum here. Whites, at the beginning, we were up at the advantage, so the model was doing pretty well until we got to here. And this was, after this point, we started to lose momentum. So let's see what moves actually got us there. So we had, I think it was the knight from, we moved the knight from D6, apologies, from D4 to F3, which was a sensible move given that the knight was under pressure here. But then what happened after that? So the bishop was developed, and you can see the advantage starting to creep towards black because we can't get this knight out of the way. If we got that knight out of the way, we would be in check. And then let's see what we did after that. So we moved our bishop to this position. And I think, you know, it's not necessarily a terrible move, but it's not a great move either. We could have put our bishop here and started developing this position, putting more pressure on this square here. And then we were putting check. Fine. We took the bishop. Again, and you can see the advantage creeping back up. And we castled. And then here was the blunder. Right? So we gave away the knight. So that was knight from F3 to E5. So let's see if we can find the reasoning trace from that. So we should be looking here, best move F3, E5. So these are all the green that you can see is the reasoning trace from the agent itself. So we'll be looking knight F3, E5. Let's see what the rationale was that the large language model gave for that move. Knight F3, E5. Here we go. So that's the move, knight F3, E5. So just to make you aware, F3 to E5. Now that's a bad move. If you know chess, you know it's a bad move because we're sacrificing the knight. And yeah, some of you might say, well, then we can just take the queen, but we're still down material if we do that because we'll lose our queen ultimately as well. So it's a bad move. What is the justification that the agent provides? So it says, after careful analysis of position, I believe the best move is F3, E5. Here's why. Control of the center. This move directly attacks the center, putting pressure on black's E5 pawn and potentially gaining control of this crucial square. So it says putting pressure on black's E5 pawn. So if you notice, I don't even believe there is a pawn in E5, but let me just double check. So here's E, and there's 5. Did we take something there? Was there something there before? Yeah, okay. So when it says putting pressure on black's E5 pawn, I think it means just taking the pawn, right? So we took the E5 pawn, which was here. So then it says piece development and positioning. The knight on E5 is excellently placed, which is complete nonsense. That's not excellently placed because we're actually in danger here. Controlling key central squares and potentially threatening black's king side. Yes, if we weren't in danger. So that is true if we weren't in danger. And even if we are, it is potentially threatening it, but we still have that rook there, which can take the knight. We can recapture the d pawn, opening up the bishop on c1 and the queen, which could lead to a powerful attack. Strategic considerations. The knight on e5 restricts black's piece movement and could be used as a springboard for a kingside attack. Now, I think what should scare you about this, or not scare you, but what you should be concerned about if you are using agents to build if you're using large language model powered agents to build applications, is level of confidence it has in its reasoning here. We can see quite clearly from the chessboard that this is a mistake. And, the computational analysis also shows us it's a mistake because we've sacrificed the knight. Yet the agent is so adamant, and in its language, it's so sure that the move it's made is the right move. And I think that this is a problem with large language models. We know about hallucinations, but I think seeing it played out in chess is a real visceral view of these hallucinations, because you see the mistake really plainly here. Whereas sometimes hallucinations can be disguised in persuasive and colorful language we've become so familiar with large language models. So you can see here that it's confident in moving this knight here, but it's wrong. It's really wrong. So the computational analysis shows that after this, the board was heavily swayed towards black. We lost a lot of points on that. And if we play this route, we will see a point where we end up sacrificing the queen. So did you see that? That was queen to d5. So let's have a look and let's see what the rationale was for that queen to d5, because quite clearly to anyone, even if you are not an expert in chess, putting your queen in double danger, so danger from the knight and danger from the pawn, doesn't make any sense. So let's see how we justified that. Let's see how the large language model justified that. So there we go. That's the move, d1 to d5, d1 to d5. So it says the rationale. After careful analysis of the position, I believe the best move is d1, d5. Here's the rationale. Control of the center. So again, it's this recurring theme of control of the center. It just believes no matter what, controlling the center is good, but doesn't seem to realize the danger around it. This move puts pressure on the central e5 square and the c6 pawn. Right, so we have the central e5 square and the c6 pawn, which is here. Which, yes, it does put pressure on it, but it's not your turn next, right? It's the black's turn. So now black is going to take that queen. Let's see if there's any other thing that stands out here, because there is a lot of information here. Here we go. So we have something about safety, and this is where it should get really interesting. The move doesn't expose our queen to immediate threats or discovered attacks. Now that's categorically untrue, but again, it says it with such confidence. It says it with such like almost self-assuredness. It's unbelievable, actually. And you can just take this situation of chess and put it into a situation where you might be asking agents to run very complex processes in your organization. And you can be sure that if it's really a truly complex problem, you might run into these same issues. And this is where hallucinations do get dangerous. In a game of chess, obviously, the only thing we lose here is the game. But in a corporate setting or in a business setting, this could amount to you losing money. So it's really important to be aware of this. And I'm going to talk a little bit about this at the end. I'm going to go into some detail about where I think agents can be useful and where I would avoid using agents. All right. So I'm not going to go into any more detail about the game, but it's just interesting to see how confident this large language model is, and indeed where it actually goes wrong with that level of confidence. Now, I'm going to try out a few frameworks. So one thing I tried to use these large language models in multi-frameworks, because I thought, you know what, it seems that just using one model by itself means that the language model doesn't quite capture or doesn't get a good understanding of the board. So maybe we can refine the responses using a multi-agent framework of some kind. So I explored two multi-agent frameworks. I explored a multi-agent framework I came up with myself, a custom framework, and I will go into more details about that in a minute. And I also explored the mixture of agents framework, and I'm going to go into more detail about that too. So we'll try both of those frameworks and we'll see if our agent can play much better at this game of chess using those frameworks. Based on the performance of just having a single large language model powering an agent, I thought that I could get a little bit of a performance uplift by combining agents into some kind of agent chain. So what I noticed when I was analyzing the rationale of the single agent is that it often would place a move and wouldn't really anticipate the counter well from the opponent. And that might be because it had poorly represented the state of the board. So moving the queen to somewhere where it thought it wouldn't be in danger, but it actually was. Or it might just be an error in logic or judgment too, moving the queen somewhere and saying that it wasn't under pressure when it clearly was. Now, how I thought to overcome this was to use some kind of prompting to do that. So I wanted to test out, okay, if we string some agents together, would it actually be able to overcome that issue to an extent? So what I did was I had 3 agents. The first one suggests a move. So we'll suggest some chess moves, not just a single move, but I think I had prompted it to suggest a variety of possible moves to make. The second agent then takes that list of suggested moves, and that list will be provided with some rationale too, and it thinks of counters that the opponent could make based on that list of suggested moves. The third agent then takes the suggested moves and the counters, and then selects the best move of the lot. Now, obviously, each agent is aware of all of the previous moves that have been made by both black and white and the state of the board. So each agent is aware of all of that. And also the agent suggesting moves at the start and the agent selecting the best move is aware of all of the legal moves. If you want to get into more details about the prompting for this, it's available in the prompts.py file that I showed you earlier when I was doing the quick code run. So you can check that out for yourself. So this is the multi-agent large language model approach that I've taken. Let's see how this runs on a live game versus the Stockfish engine. So I've explained to you my custom multi-agent framework. I'm going to show you how to get that set up in the script, and then I'm actually going to run a chess game with that. So again, you navigate to the homemade.py script. This is where the multi-agent engine is set up. So you can see this class here, LLM multi-agent. And just to show you, this will be working on the Claude 3.5 Sonnet model. You have the first prompt here. So this is the master prompt. And that is where we're asking the model to come up with some moves. So we have chess master 1 here. And then master 2 is where we're asking the model to critique those moves and tell us possible responses that black could make, or that the opponent could make, because it doesn't have to be black. It could be white if we're starting as black. And then we have response 3, which takes all of that information from master 1 and master 2 and generates the best move. And this is all working off the Claude Sonnet model, as I mentioned before. So to get this set up, what we want to do is we want to copy that class, enter the config YAML file, and then where it's on the engines, where we're describing the name of the engine, what you want to do is replace this with the engine you want to run. So in this case, it's the LLM multi-agent. And then hit save. Once you've hit save on that, we can navigate back. And we want to exit the chess engine. So we hit exit on that. And then we want to run Python light chess. So we're just restarting the chess engine, Python light chess bot.py. And by rerunning that, we restart the chess engine with the new configurations. On the left-hand side here, if I scroll back to play, once the engine is up and running, so we can see configurations have been checked and we're all up and running, we can play again with the computer. So this time around, I'm not going to do a running analysis of the chess game simply because we're using a multi-agent framework. So this does take a bit longer to execute each move. However, I will do a post analysis using the computational analysis feature again for help. And we'll discuss some of the results if they do look interesting. let's have a look at the analysis board to see if that insight tells us anything about the way this multi-agent framework played as opposed to the single agent. So as I pull up the analysis board, what I expect to see here is kind of a similar pattern in the sense of at the beginning, things were a little bit more even, but at some point, black just took over. And I think that's actually filling out now. Right, so you can see we start off as white with the advantage, and then at some point, the model makes a crucial mistake, and it's all black from there. And actually, this is even more dramatic than the first game. So let's see what happens at that point. So if we go to that point, we can see the momentum swings here when, let's see what it says. So it's saying the momentum swing was the bishop move here, which, to be fair, I don't think was the worst move, but not the best move either. And then after the bishop move, black moves its knight away. Bye. And then we continue. So yeah, these aren't terrible moves, but it's suggesting the momentum swings in favor of black. Right? So we lose our bishop. So that was a mistake, actually. Because what we didn't do is we didn't move the bishop into safety or cover it. So what we could have done is we could have covered this bishop by maybe bringing our queen into play and covering the bishop there. You could also move the knight here and cover the bishop, which I wouldn't do ideally because having your knight stuck on the wing isn't really ideal. Well, we didn't. So we instead moved the knight from B6, from B to C3. And that led to our bishop being lost. And that was giving away material to the queen. Let's continue on. So we developed the queen. And then black put the queen under pressure. And there, that was the fatal move. Because as soon as we did the queen h5 to g6, we put the queen in danger. So let's look for that move, h5 to g6, and let's see why, or what was the rationale behind that h5 to g6 move. Maybe we can do a control F and find it. h5 to g6. So there are a lot of moves here. Let's see if we can do this. h5 to g6. There's 24 of them. Right, here we are. So it should be, here we go, found it. So this is our h5 to g6. So this is what it says, the rationale. And this is after passing through that multiple agent framework. After careful analysis, I believe the best move is h5, g6. Queen takes g6. That's what we've done here. That was that move. Just to show you again, queen takes g6. This aggressive move puts immediate pressure on black's king side and exposes the black king. It removes the pawn shield, creating significant weaknesses around the black king. Yeah, I guess so. I guess that's one way of looking at it. If black recaptures with h7, g6, so what's h7, g6? Whoops. Get back to where we were. But saying if black recaptures with h7, g6, h7, g6, let's see what happens. If black recaptures with h7, g6, we can follow up with e3, g5, threatening a devastating check on h7. So we can follow up with e3, g5. So we've got, this is e3, bishop e3 to g5. And that is not the case. I think it's assuming, yeah, that's not even a legal move. So it's saying if black recaptures with h7, g6, which I believe is this move, and I think black did do that. So we've gone h7, oh, that's f7, apologies. So h7 would be here. to G6 there, but it did F7. But anyway, if it did that, then what it's saying is we could follow up with E3. And this is our bishop here, E3 to G5, which would be here, threatening a devastating check on H7. Well, we're talking about H7, a devastating check on H7, which is there. So that doesn't even make sense as logic on a chessboard. And, quite clearly what's happening there is the agent framework has broken down and it's not making any sense. This is sounding confident once again, but actually when you get into the details of it, it's not a good move. And ultimately led us to lose this game because we lost our queen at that point. And then from there, it was just utter devastation. And it did actually try to follow up with that. What was that? E3 to G5. And you can see there was no check available there. There's the king, and there's no check available. So you can see that there's no check available there. So the multi-agent framework didn't do too well. Let's see what we can do with mixture of agents next. The final approach I tried with getting these LLMs agents to play chess was to use this mixture of agents approach. So there's a paper that suggests that using a mixture of agents actually enhances the capability of large language models. So there's details in this paper and there's data to suggest that using a mixture of agents can outperform just a single large language model on certain benchmarks. And I'm not going to go into the details of this paper, but it is linked in the description to this video if you do want to explore that further. The paper does suggest particular models for working with this mixture of agents framework, and they suggest a way of putting the agents together for the approach. And I'm going to go into how I've approached it next. I want to demonstrate how I have implemented mixture of agents for this chess problem. So mixture of agents suggests a very particular agent structure. So what you have are agents that propose, and then an agent at the end that aggregates all of those proposals. And those proposals are filtered through layers to refine the proposals until you get to the aggregation layer. So I have a very simple mixture of agent structure. I have an initial proposal layer, and each agent is powered by GPT-4. Each agent is tasked with coming up with a chess move, given the current state of the chessboard, that it believes is going to be the best move. Ideally, each of these are going to be different. Then that proposal is passed on to the next layer, which here the agent is tasked with taking that proposal and refining it. And this agent is also aware of the chessboard. And its job is to take what the first agent did and refine it. And hopefully we get a better solution from that refining process. And this is done across all of these agents. And then finally, we have an aggregation layer. And the job of this aggregation layer is to aggregate all of the refined proposals and deliver the best chess move based on those refined proposals. This is how I've implemented the mixture of agents approach. It does say in the paper that you can use the same model across the different layers. I've used GPT-4o because the paper suggests it's a good model for proposing. I've used the Claude 3.5 Sonnet model, being the best model available from Claude right now, and some suggest that it even outperforms GPT-4o. So it suggests in the paper that highly intelligent models might be better for aggregating than the less intelligent models. So I've chosen Claude 3.5 Sonnet on that basis. I will say that 3.5 Sonnet obviously hasn't been tested in the mixture of agents paper because it came out after the paper came out, I believe. But this is my approach to the mixture of agents problem, to try and see if we can get better performance out of this chess engine. All right. Next, I'm going to show you how the mixture of agents actually performed against our Stockfish chess engine. All right. Right. Now that we have an understanding of how the mixture of agents framework works, let's set up our script to run a mixture of agents bot. We'll do this again by navigating to homemade.py. I already have the class set up for mixture of agents. So you can see that here. And I'll show you quickly how that works in the script. So under our search method, we have our proposer agents. So we have proposer agents in layer 1. You can see all 3 of them there. And these are running off GPT-4o. And notice the get LLM responses, the OpenAI one, because we're running off GPT-4o. And then we have our proposers in layer 2. And remember, these act to refine the proposals in layer 1. And these are again working off GPT-4o, just as the diagram I showed in the previous section. So you've got all 3 of those operating. And notice they're all running off the OpenAI get LLM response as well. And then we concatenate all of our proposals from layer 2. So you can see that all concatenated there. And then that feeds in to the final aggregator model, which will be the Claude 3.5 Sonnet model. And that will act to aggregate all of our proposals. And then we deliver our final move here. And that's the move we play. So that's how the mixture of agents setup works in my script. Now we want to set it up so we can run that server on Lichess. And what you want to do is you want to grab that mixture of agents class, head to config.yaml, and replace the agent here with your mixture of agents class and hit save. So make sure it is saved across the entire project. You hit save. And then when you're ready, head back to your chess engine. Let's scroll right down to the bottom. Exit the chess server. And then we run it by running Python lichess bot pi once again. And you'll hit run on there. And that will get your chess engine started with the mixture of agents framework. And you're ready to accept challenges. So once again, this does take some time to run through. This actually takes even longer than the previous one because there's a lot more steps in this mixture of agents framework. So I am going to run it and I'll do the analysis post hoc after everything's run. So it's another checkmate to the chess engine. Let's do a computational analysis of the board and see where we went wrong, although I believe it is quite obvious. Let's have a look. And let's request a computational analysis. So you can see from the computational analysis that we were doing quite well. We're maintaining an advantage up until a certain point. And I think naturally as well, being white, you are going to maintain that advantage because you have the first move. But inevitably, there came a swing. I think that doesn't tell you the turn. That's turn 1, turn 2, turn 3, turn 4, 5, 6, 7, 8. So the swing was on move 8. let's have a look and see what that was. So they're saying we lost the advantage when we brought the pawn into this position. And I don't necessarily agree that that is necessarily a bad thing, bringing the pawn into that position. I think well, we're covered there by the knight, but obviously, that pawn is under threat from black's knight too. So let's progress and see. So that pawn was taken, and it doesn't really make sense to then lose our knight here as well. So we lose more material by doing that. So I guess that's why it was a bad move. But again, not the end of the world. But then we do sacrifice our knight and end up losing more material than we should. So that's not a good move. Let's continue on. And ultimately, that is what loses us. That's the beginning of us starting to lose the game, because from here, black decides to develop the queen. Again, there's a needless sacrifice of a bishop. We gain the knight, but we're not really thinking ahead this time around. So we lose the bishop. So at this point, any chess player would see that we are about to get the checkmate, because you can see the bishop lining this square up. And that's a danger square there, because the queen can come in and checkmate. So what's interesting is, as a chess player, you would anticipate this, and you would do something to stop this happening. So you might go for a kingside castle there, and that's what we're suggesting. But what the language model decided to do was progress the pawn. And I'd like to see the rationale for that. So that is pawn e5 to e6. So let's see if we can find that. e5 to e6. Let's see what the rationale was for progressing the pawn from e5 to e6. Here we go. So here's the rationale from the aggregator. Analysis of the proposed moves and the current board state. The move e5 to e6 emerges as the strongest option. This move is both aggressive and strategically sound for several reasons. Disrupts black's pawn structure. By pushing the pawn to e6, we force black to make a difficult decision. So we already know that's not true, because black is focused on getting the checkmate here. So that's not true. And then it goes on to talk about several situations about if black captures something. I wonder if it mentions at all the possibility for checkmate. So it talks about opening lines for our queen. Let's just see. Right, black's queen, here we go. While not directly attacking black's queen on h4. So it is aware that black's queen is there on h4, but it's not aware that it can actually checkmate the king, which is interesting. This move creates counterplay that black must address, potentially forcing them to use a move to retreat their queen rather than continue their attack. While moves like queen 1 h5 or queen 1 g4 were also considered, they allow black to weaken their kingside with g6 without immediately gaining material or positional advantage. The move e5 e6 creates more lasting pressure and positional gains. So again, this just kind of sounds like a lot of nonsense, because really the imminent threat here is on our king. That's the imminent threat. The imminent threat is the queen moving from h4 to f2, and that's a checkmate if the queen does that, which finally ended the game, actually. So that was a checkmate. So it's interesting, because we do give these models an awareness of the state of the board, and I'll show you what that looks like really quickly. So it's a series of moves that have been taken. So this is the board state. For each turn, the model is aware of the state of the board, and it's aware of all of the moves that it's made up until that state, and it's aware of all of the moves that its opponents made, and it's aware whether it's aware of itself, so it knows it's black or white. But it doesn't seem to actually understand the board, and you can see that by the choice of moves it makes. Now, I want to get into a bit more detail about why I think this is and how this has implications on building agent frameworks for other applications, whether that's kind of in business or for your own personal life or whatever you want to build agent frameworks or not build it, whatever you want to apply agents to. I think understanding the limitations here using this chess example will be important for you to make sure that you're building agents in the right places instead of believing that agents can somehow solve all of the problems that human beings can solve right now. So I'm going to get into that in a bit more detail next. I gather that the people that watch this video are going to fall into two camps. Those that already knew that large language model powered agents would be no good at chess, and those that didn't know that large language model powered agents would be no good at chess. I want to dive into this topic a little bit here. The first thing is to understand why large language model powered agents are not good at chess. So if you pay attention to what I have on screen, what I've done is I've asked Perplexity to tell me what the game tree complexity of chess is. So to understand what we mean when we say game tree complexity, you can think of this as all of the possible sequences of a chess game. So from start to finish, from start to checkmate, let's say. So that's estimated to be 10 to the power of 123. That's an absolutely huge number. It's unimaginably large, that number. And just to give you the source here, I use Perplexity because it does give us sources. This is from the chess Wikipedia page. So we estimate the game complexity to be 10 to the power of 123. What does that mean for large language models? That means that as you progress through a chess game, there are so many possibilities of the sequence of moves to end up at any given state in a game. So, for example, if I navigate back to my code and I bring up for the last game I played, if we go to the game state JSON, this represents one sequence of games. This represents one game sequence, start to finish. So that was for the mixture of agents framework. What we're saying here is there are 10 to the 123rd power possible sequences here that we could have in the game of chess. That's what it's estimated at. There is no way that a large language model is going to have even a fraction of those in its training data. And we know this because if you look at the state-of-the-art large language models, we know that they were trained across the entire internet. How many websites exist on the internet? It's estimated that there are about 1.1 billion active websites. Or actually, it says only 18% of these websites are active and 82% are inactive. But let's just take the total estimate of 1.1 billion websites across the world. So even if you train your large language model on every website that there is available to you on the internet and probably every book, you will not cover that game space complexity for chess. You will never cover it. So what does this mean for the large language model? It means that throughout a chess game, it will begin to encounter games that it has never seen before. They don't exist in the training data. They're completely novel. And because it encounters games that it hadn't seen before, remembering that large language models take what they've seen before, are trained on what they've seen before, and therefore become expert at, given a prompt, being able to predict what comes next because they've seen it before. They have never seen those chess games. So being able to predict what the best next move is, it has no idea. It's never seen that game before. So essentially what you're asking a large language model powered agent to do when you ask it to play chess is being able to reason based on a state of a chessboard that it's likely never seen before. And what I think getting them to play chess demonstrates is that these large language model powered agents don't really have the ability to reason. They don't really have the ability to reason, especially when things aren't in the training data. So they're almost parroting back to you what's in the training data rather than reasoning. Now, that doesn't mean that large language model powered agents aren't useful. They are useful, but you've got to make sure that the application that you are using makes sense. So there are a few areas where I think if you're using large language model powered agents, that you could run into some problems. So I've written a few of them down here. So the first one is anything where there is a combinatoric, apologies, I always get that one wrong, but anything where there is a large number of possible combinations of outcomes. So a game like chess is an example of that. Another game would be something like Go. Maybe even some video games as well. There are a large number of possible outcomes for what somebody can do in a video game or what a video game character can do. The next thing is anything novel. So if you're working in the legal profession and you're dealing with something that is kind of like a novel, legal, ethical case, you might start to run into issues when it comes to using large language model powered agents. Let's say you have a legal chatbot that needs to come up with some kind of novel legal or ethical reasoning. You might run into some issues there. The other obvious one is scientific research. So at the cutting edge, scientists are trying to discover new, they're trying to make new scientific discoveries at the cutting edge. Obviously, this stuff is not going to be in any training data corpus that a large language model is going to have. So asking a large language model to reason about new scientific discoveries could lead to those types of hallucinations that we saw on the chessboard. And I guess a more obvious one is also code bases. So I remember using GPT 3.5 early on to help me with certain aspects of the boilerplate code from things like scikit-learn, and it would always hallucinate the methods on certain classes in scikit-learn. And that's because it hadn't yet been trained on the most up-to-date library for scikit-learn. If you're a company that is working with a massive internal code base, and that internal code base is proprietary, so it hasn't actually been seen in the public, it's likely that an OpenAI model or any state-of-the-art large language model hasn't been trained on your code base. So you already know that having an agent to work on that code base is likely going to lead to a lot of hallucinations. And I guess people are trying to figure this out by using things like RAG for in-context learning, but that comes with its own problems when you've got such a massive code base. So in short, I do believe there is still a place for large language model powered agents. I think where you're dealing with problems that are not novel. So a good use for large language model powered agents is web search, for example. So Perplexity actually does that. It uses a large language model to understand your question and then uses some tools in the background to go and actually search and index web pages for you and return results. I've also built custom web search agents using large language models as well. Connecting to APIs. So APIs have a defined structure, and large language models are great at parsing language from the unstructured form, to the structured form. So we can connect to APIs. I think that's also a fantastic use case for agents. And now a lot of the large language models are becoming really good at producing JSON formats consistently. And that's the key thing there for actually parsing outputs to APIs to be able to connect large language models to APIs for an agent purpose. So I think that's also another fantastic use case. If you enjoyed this content, give the video a thumbs up. It'll be good to hear your opinions about the limitations of large language model powered agents. It would also be good to hear your opinion about what you've seen on the chess demonstration that I've done. Feel free to comment any opinions in the comment section. And remember, if you like this content, subscribe to the channel for more AI engineering content. I will see you in the next video.